A telescope 1 million miles from Earth just shattered everything we believed about the universe. Galaxies that should not exist. Black holes, too massive for their age. A cosmic runaway tearing through space at 2 million miles per hour. Over the next 2 hours, we will journey to the edge of time itself. We will witness the first light that ended the cosmic dark ages, explore worlds where diamonds rain from carbon skies, and confront discoveries so strange that scientists are questioning whether our entire model of reality is broken. If you enjoy this journey, hit like and subscribe. Now, prepare yourself. We begin. 290 million years after the Big Bang, something impossible appeared. A galaxy, fully formed, bright, chemically complex. Scientists have confirmed its existence using the most powerful telescope ever built. They named it after a sacred river in the Himalayas, and it breaks nearly every rule we thought governed the early universe. To understand why this discovery sent shockwaves through the scientific community, you need to understand what we expected to find. The standard model of cosmology told us a clear story. After the Big Bang, the universe was a hot, chaotic soup of particles. Gravity slowly pulled matter together over hundreds of millions of years. The first galaxies were supposed to be small, messy, irregular clumps. They would take billions of years to organize into the beautiful spiral structures we see today. Our own galaxy, the Milky Way, took roughly 10 billion years to develop its sweeping spiral arms. 10 billion years of collisions, mergers, and gradual organization. This distant galaxy did it in a few hundred million. When astronomers pointed the James Webb Space Telescope at a tiny patch of sky no bigger than a grain of sand held at arm's length, they found something that should not be there. The galaxy contained 10 billion stellar masses worth of material. It had already organized that material into a structured disk, and its chemistry revealed oxygen and other heavy elements that require multiple generations of stars to produce. Here is what makes this even stranger. Heavy elements like oxygen do not exist at the beginning. The Big Bang only created hydrogen, helium, and trace amounts of lithium. Everything else, every atom of carbon in your body, every molecule of oxygen you breathe, was forged inside stars and scattered into space when those stars exploded. For a galaxy to contain significant oxygen, stars must have already lived and died, multiple generations of them. Yet this galaxy existed when the universe was only 2% of its current age. The implications are staggering. Either stars formed and died much faster than we believed possible, or something about our understanding of the early universe is fundamentally wrong. Scientists working on this discovery have called it extraordinary. They used 9 days of telescope time to gather the data. 167 hours of imaging focused on a patch of sky, so small that if they had pointed the telescope just a fraction of a degree in any direction, they would have missed it entirely. Think about that. This galaxy was found by accident, in a tiny random sample. If such a mature galaxy exists in such a small slice of sky, how many more are out there? The math suggests there should be many, and that terrifies cosmologists. The team that made this discovery was not looking for trouble. They were conducting a deep survey called the James Webb Space Telescope Advanced Deep Extragalactic Survey. They expected to find primitive, chaotic structures. Instead, they found a galaxy that looked like a younger twin of our own cosmic home. One researcher described it this way. Imagine expecting to find a newborn infant and instead discovering a fully grown adult. The physics of growth simply do not allow for that, unless the physics is wrong. This is confirmed science, published in peer-reviewed journals. The galaxy exists, its chemistry is real, and it forces us to confront an uncomfortable truth. The universe was capable of far more rapid assembly than anyone anticipated. Somehow, matter organized itself with breathtaking speed in the cosmic dawn. But here is what keeps astronomers awake at night. This galaxy is not alone. It is not even the strangest thing the telescope has found. Across the early universe, Scattered through image after image, observers noticed something even more puzzling. Tiny red points of light, hundreds of them, objects so compact and so bright that no existing theory could explain them. And when scientists finally figured out what they were, it changed everything we thought we knew about black holes. In the summer of 2022, the James Webb Space Telescope sent back its first scientific images. Within weeks, astronomers noticed something strange. Scattered throughout the observations, appearing in nearly every deep field image, were tiny red points of light, small, compact, unusually bright, and completely unexplained. Scientists gave them a simple name: little red dots. At first, researchers assumed they were distant galaxies. Old galaxies tend to appear red because their stars have aged. The light from ancient stellar populations shifts toward warmer colors as the hot blue stars die off and leave behind cooler red ones. This is well understood physics. But something did not fit. These objects were too small. When astronomers tried to resolve them into recognizable galaxy shapes, they could not. The little red dots remained stubbornly compact. They appeared to be less than 2% the diameter of the Milky Way. If they were galaxies packed with enough stars to explain their brightness, those stars would need to be crammed together at impossible densities. The night sky of such a galaxy would be dazzlingly bright. You would see millions of stars with your naked eye. The stellar density would violate everything we know about how gravity organizes matter. So the mystery deepened. What were these objects? One possibility emerged quickly. Perhaps the light was not coming from countless stars, but from a single source, a supermassive black hole. When black holes feed on surrounding gas, they can outshine entire galaxies. The matter spiraling into the black hole gets compressed and heated to millions of degrees, producing enormous amounts of radiation. This explanation seemed promising. It would account for the brightness without requiring impossible star densities, but it created a new problem. Supermassive black holes that active should blast out X-rays and radio waves. Astronomers looked for those signals. They found almost nothing. The little red dots defied every category. Too bright to be normal galaxies, too quiet to be typical active black holes. They existed in a strange middle ground that our models could not explain. And there were so many of them. Hundreds have now been identified. They appear abundantly in observations of the early universe from around 400 million to 1 billion years after the Big Bang. Then, mysteriously, they seem to vanish from the cosmic record. Whatever these objects are, they existed for a brief window of cosmic time. They appeared suddenly, remained visible for perhaps 500 million years, and then disappeared. For 3 years, astronomers argued about their nature. Some favored the idea that they were dust-shrouded galaxies. Others insisted they must contain hidden black holes. The debate grew heated. Competing theories multiplied. But without better data, no one could prove anything conclusively. Then, in early 2025, researchers at the University of Copenhagen announced a breakthrough. They had analyzed the little red dots for 2 years, using the most detailed spectroscopic data available. Their conclusion was startling. The little red dots are young black holes, but not the kind anyone expected. These black holes are wrapped in dense cocoons of ionized gas. They are actively consuming that gas, generating enormous heat that shines through the cocoon. The radiation passing through gives them their distinctive red color, and the cocoon makes them appear far more massive than they actually are. The researchers found these black holes are about 100 times less massive than previous estimates suggested. They are not billion solar mass monsters. They are smaller, hungrier, and growing fast. This discovery solves one puzzle, but opens another. If these are young black holes in a feeding frenzy, we may be watching the birth of the supermassive black holes that anchor every major galaxy today. We are seeing cosmic infants in their growth spurt. But some scientists believe the truth is even stranger. They think the little red dots might not be simple black holes at all. They might be something that has never been seen before. What if the little red dots are not galaxies? What if they are not typical black holes either? What if they are something completely new? In late 2025, researchers proposed a radical idea. The mysterious red objects scattered across the early universe might be an entirely new type of cosmic structure. They called them black hole stars. The concept is as strange as it sounds. Imagine a black hole sitting at the center of an enormous sphere of hot, dense gas. The black hole is actively pulling matter inward. As gas falls toward the event horizon, it accelerates to incredible speeds. The compression generates temperatures of millions of degrees. This releases staggering amounts of energy. But here is the critical part. Only a tiny fraction of the infalling gas actually crosses the event horizon and disappears forever. Most of it gets blasted back out. The intense radiation pushes the majority of the material away from the black hole before it can be swallowed. Scientists sometimes describe black holes as messy eaters. They consume far less than they appear to grab. The rejected gas forms a dense, turbulent atmosphere surrounding the black hole. From a distance, this entire structure, the black hole plus its gas envelope, looks like a single, gigantic star. Except it is not powered by nuclear fusion like normal stars. It is powered by gravity and the violent compression of infalling matter. One research team analyzed a particularly extreme little red dot they nicknamed the cliff. Its spectrum showed something unprecedented. The object appeared to have so much atmosphere that it could not be explained as a collection of ordinary stars. It seemed to be one gigantic, very cold star. But it was not cold because it lacked energy. The coldness came from the gas envelope surrounding the black hole. The dense cocoon absorbs the highest energy radiation and re-emits it at longer wavelengths, making the object appear red and relatively cool on the surface, even while tremendous heat rages at its core. If this interpretation is correct, we have discovered a missing link in cosmic evolution. Here is why this matters. Astronomers have long wondered how supermassive black holes grow so massive so quickly. Normal feeding processes should take billions of years, but we find billion solar mass black holes existing less than 1 billion years after the Big Bang. The math does not work. Black hole stars might solve this problem. If young black holes can wrap themselves in dense gas cocoons, they can feed much faster than exposed black holes. The cocoon shields the growing black hole from its own radiation, allowing it to consume material more efficiently. The gas provides the fuel, the black hole grows, and over several 100 million years, it can balloon from a modest seed into a cosmic giant. This would explain something else that puzzled astronomers. The little red dots appear everywhere in the early universe, but vanish about 1 billion years after the Big Bang. If they represent a temporary phase of black hole growth, that makes sense. The cocoon eventually gets consumed or blown away. The feeding frenzy ends, and what remains is a mature, supermassive black hole sitting quietly at the center of a galaxy. We would never see the black hole star phase in the modern universe because that stage ended billions of years ago. The James Webb Space Telescope is looking back in time, catching these objects during their brief but crucial growth period. This is still a theory. Scientists are debating it intensely. More observations are needed to confirm whether black hole stars truly exist. But the evidence is compelling. The spectral signatures, the size, the brightness, the timing, everything fits. If confirmed, this discovery would reshape our understanding of how galaxies form. The supermassive black holes at the centers of galaxies would not be passengers that grew alongside their hosts. They would be the seeds around which galaxies assembled. But the strangeness does not stop there. Even setting aside the little red dots, astronomers found something else troubling in the early universe. Galaxies that are simply too big. The universe has a speed limit for growth, or so we believed. When the James Webb Space Telescope began surveying the distant cosmos, it revealed galaxies far larger and more luminous than any model predicted. These were not subtle outliers. They were 10 to 100 times more massive than the physics should allow. To grasp why this is a crisis, consider how galaxies are supposed to form. After the Big Bang, the universe was almost perfectly smooth. Matter was spread nearly evenly in all directions, but not quite perfectly. Tiny quantum fluctuations during the first fraction of a second created microscopic variations in density. Some regions had slightly more matter than others. Gravity amplified these differences over time. Denser regions pulled in more material, growing slowly but steadily. The first dark matter halos formed. Gas collected within these halos. Stars ignited. Gradually, over hundreds of millions of years, the earliest galaxies assembled. The key word is gradually. The standard cosmological model predicts a specific rate of growth. Matter can only accumulate so fast because gravity operates at a fixed strength, and the universe was expanding, working against the pull of gravity. According to these calculations, the first billion years should have produced small, faint, chaotic structures. Finding anything as bright and organized as the modern Milky Way should be impossible until several billion years had passed. The telescope disagreed. In its first year of observations, the James Webb Space Telescope found bright galaxies everywhere in the early universe. Not just a few anomalies, but a consistent population of objects that challenged expectations. Some appeared as luminous as mature galaxies, despite existing when the universe was only 3% of its current age. The initial reaction was disbelief. Many astronomers assumed the measurements were wrong. Perhaps the telescope's instruments needed better calibration. Perhaps the distance estimates were incorrect, placing nearby objects at cosmic distances. Teams around the world scrutinized the data. They recalibrated. They reanalyzed. The results held. One particularly dramatic example was a galaxy found at a redshift, indicating we see it as it appeared just 400 million years after the Big Bang. It contained billions of stellar masses worth of stars. For context, our own galaxy contains roughly 200 billion stars, but took over 13 billion years to assemble them. How can a galaxy accumulate so much material so quickly? Several explanations have been proposed. Perhaps star formation was more efficient in the early universe. Perhaps the first stars were more massive and luminous, making young galaxies appear brighter than their actual mass would suggest. Perhaps dark matter behaved differently at early times. Each explanation has problems. Higher star formation efficiency requires conditions we do not observe elsewhere. More massive early stars would leave distinct chemical signatures that we have not found. Modified dark matter would conflict with other observations. Some researchers wondered if the discovery meant the Big Bang happened earlier than we thought. If the universe were older, there would be more time for growth. But the cosmic microwave background radiation, the afterglow of the Big Bang, provides an extremely precise age estimate. The universe is 13.8 billion years old. This is not negotiable. So we face a genuine puzzle. The universe produced large, bright, mature galaxies far faster than our models allow. Either something accelerated growth in ways we do not understand, or our models are missing something fundamental. And the crisis extends beyond galaxies. The same observations that revealed impossibly massive galaxies also revealed something even more disturbing. Supermassive black holes that dwarf their host galaxies. Objects so oversized that they break a relationship astronomers thought was universal. The rules are failing, and no one knows why. Spiral galaxies are supposed to be old. The beautiful pinwheel structures we see in images of nearby galaxies represent billions of years of evolution. Our own Milky Way took roughly 10 billion years to develop its graceful spiral arms. The process requires time, stability, and the right conditions. First, a galaxy must accumulate enough mass. Then it must settle into a rotating disk. Density waves must propagate through that disk, compressing gas and triggering star formation along curved paths. Gradually, over cosmic ages, the spiral pattern emerges. This is settled science. Dozens of simulations confirm the timeline. Spiral structure requires patience. So, when astronomers found a fully formed spiral galaxy just 1.5 billion years after the Big Bang, they did not know what to say. The galaxy is called Alaknanda, named after a river in the Himalayas that is one of the twin sources of the sacred Ganga River. The name carries deep meaning. In Hindi, Mandakini, the other twin source, is also the word for the Milky Way. Alaknanda looks shockingly like our cosmic home. It has sweeping spiral arms, a defined disk structure, and rapid star formation concentrated along the spiral pattern. These are features astronomers associate with mature, evolved systems, not with galaxies existing when the universe was roughly a tenth of its current age. The discovery was made possible by gravitational lensing. A massive cluster of galaxies sits between Earth and Alaknanda. The cluster's gravity bends and magnifies the light from the distant spiral, acting like a cosmic magnifying glass. Without this natural amplification, the galaxy would be too faint to study in detail. Using this magnified view, researchers examined Alaknanda with unprecedented clarity. They confirmed the spiral arms are real, not an artifact of distorted light. They measured the rotation of gas and stars. They calculated the total mass. The galaxy contains roughly 10 billion stellar masses. It assembled and organized this material into a beautiful spiral disk in just a few 100 million years. By cosmic standards, that is extraordinarily fast. The team that made this discovery described their findings carefully. They noted that the early universe was capable of far more rapid galaxy assembly than anyone anticipated. Somehow, this galaxy pulled together enormous amounts of material and organized it into stable structures almost immediately. But how? One possibility involves cold gas flows. If steady streams of cold gas funneled into the young galaxy without violent disruptions, density waves could have established themselves quickly. The galaxy would have had fuel for rapid star formation and the smooth conditions needed for spiral arms to develop. Another possibility is more unsettling. Perhaps spiral galaxies do not require as much time as we thought. Perhaps our simulations are missing something about the physics of galaxy formation. Alaknanda is not alone. The James Webb Space Telescope has found several surprisingly mature disk galaxies at great distances. These objects keep appearing, challenging the narrative that early galaxies were chaotic and irregular. One massive spiral, nicknamed the Big Wheel, existed within the first 2 billion years of the universe. Its structure is so clean and organized that researchers expected it to be elliptical, a smooth blob of stars. Instead, it displays beautiful spiral arms, similar to those in our local neighborhood. The implications ripple outward. If galaxies can form and mature this quickly, what else might the early universe have accomplished? The answer involves objects at the very hearts of these galaxies. Objects that are even more out of place than the galaxies themselves. Supermassive black holes, growing without restraint. At the center of nearly every large galaxy sits a monster. Supermassive black holes contain millions or even billions of times the mass of our star. They anchor galaxies, influence star formation across thousands of light years, and when they feed, they can outshine everything around them. In the nearby universe, these black holes follow a pattern. The mass of the central black hole scales predictably with the mass of its host galaxy. Bigger galaxies have bigger black holes. The ratio is remarkably consistent. For every 1,000 units of stellar mass, there is roughly 1 unit of black hole mass. This relationship suggests that galaxies and their black holes grow together, evolving in lockstep over cosmic time. The physics seems to enforce a balance. When the black hole grows too fast, its radiation heats surrounding gas and slows star formation. When stars form too quickly, they consume the gas the black hole needs to feed. This elegant dance was considered one of the best understood aspects of galaxy evolution. Then the James Webb Space Telescope looked at the early universe. What it found broke the pattern completely. In distant galaxies, Supermassive black holes are oversized, dramatically oversized. Instead of a 1,000-to-1 ratio between stellar mass and black hole mass, astronomers found ratios of 100-to-1, sometimes 10-to-1. In extreme cases, the black hole mass equaled the total stellar mass of its host galaxy. These black holes are not slightly larger than expected. They are 10 to 100 times more massive than the relationship predicts. A team led by researchers at Harvard and the Smithsonian analyzed 21 supermassive black holes in galaxies ranging from 12 to 13 billion light-years away. Each one violated the local scaling relationship. The statistical analysis confirmed this was not a fluke. These early black holes are genuinely overmassive relative to their host galaxies. The discovery creates a profound puzzle. How did these black holes grow so large while their galaxies stayed small? One explanation involves timing. Perhaps in the early universe, black holes grew first and galaxies assembled later. The black holes would have consumed available gas before stars could form, keeping galaxies small while the black holes ballooned. But this raises new questions. What created such massive black hole seeds in the first place? Normal stellar collapse produces black holes of perhaps a few dozen solar masses. Growing from there to millions or billions of solar masses through feeding alone would take longer than the universe's age at that time. Some researchers propose that the first black holes formed through direct collapse. Instead of starting as stellar remnants, they emerged when enormous gas clouds collapsed directly into black holes without ever becoming stars. This would create heavy seeds, perhaps 100,000 solar masses or more, giving the black holes a head start. The James Webb observations support this theory. If black holes started massive and grew faster than their galaxies, the oversized ratios make sense. Over billions of years, the galaxies would catch up, establishing the balanced relationship we see today. But confirming this requires finding even smaller black holes at even greater distances. If heavy seeds are real, there should be a population of intermediate objects between the primordial seeds and the monsters we observe. The telescope continues searching. Each observation pushes deeper into cosmic history. Each discovery reveals more black holes that should not exist. And among these impossible objects, scientists found one that defied every limit, a black hole eating faster than physics allows. Every black hole has a speed limit. As matter falls toward a black hole, it compresses and heats up. The resulting radiation pushes outward against the infalling material. At some point, the outward pressure from radiation equals the inward pull of gravity. This balance point is called the Eddington limit. Beyond this limit, a black hole cannot consume more material. The radiation it produces blows away the food before it can be swallowed. The black hole effectively chokes on its own brightness. This limit is fundamental. It emerges from basic physics, and it sets a maximum speed for black hole growth. Even feeding continuously at the Eddington limit, a black hole takes hundreds of millions of years to grow substantially. In November 2024, astronomers announced they had found something that appeared to violate this limit spectacularly. Using the James Webb Space Telescope, researchers examined an ancient galaxy known to host an intense X-ray source. The galaxy existed just 1.5 billion years after the Big Bang. At its center was a supermassive black hole in a feeding frenzy. The data showed outflows of gas unlike anything ever observed. The speed and scale of these outflows indicated the black hole was consuming matter at more than 40 times its Eddington limit. 40 times. Not a small excess. A massive violation of what physics says is possible. If accurate, this single feeding episode could explain most of the black hole's observed mass. Instead of growing steadily over billions of years, it might have bulked up in a cosmic instant. The discovery triggered excitement and skepticism in equal measure. Some researchers saw it as evidence for a completely new feeding mechanism. Others suspected something was wrong with the measurements. In early 2025, a different team revisited the data. They found the original measurements had been distorted by dust. Dust absorbs and scatters light, dimming the signal that reaches our telescopes. If you do not account for dust properly, you can dramatically underestimate a black hole's true mass and misinterpret its feeding rate. When the team corrected for dust extinction, the picture changed. The black hole was not eating at 40 times the Eddington limit. It was feeding at a rate consistent with the theoretical maximum. Still impressive, but not physics-breaking. This correction sounds like the end of the story. The extreme claim turned out to be a measurement error. Case closed. But the implications extend further. If dust misled astronomers in this case, it might be misleading them in many others. The newly discovered class of objects called little red dots are all surrounded by complex dust environments. Their true properties might be systematically mismeasured. Some black holes we think are impossibly massive might actually be smaller. Some we think are feeding normally might be growing faster than we realize. The lesson is humbling. Even with the most powerful telescope ever built, interpreting signals from the early universe remains extraordinarily difficult. Dust, distance, and cosmic expansion all distort what we see. Scientists must remain cautious. Every extraordinary claim requires extraordinary verification. But one discovery from the James Webb telescope required no correction. One object was so dramatic, so undeniable, that its very existence validated 50 years of theoretical predictions. A supermassive black hole ejected from its own galaxy, now racing through space faster than almost any object ever observed. Something enormous is tearing through space. A supermassive black hole weighing 20 million times the mass of our star. Moving at 2.2 million miles per hour, trailing a 200,000 light-year wake of newborn stars behind it. This is not science fiction. This is confirmed observation. The James Webb Space Telescope has provided the definitive evidence. Scientists first noticed something strange in 2023 while examining images from the Hubble Space Telescope. They saw a thin line extending from the center of a distant galaxy. At first, they thought it might be an artifact, a glitch in the camera or a cosmic ray strike, but the line persisted in multiple observations. It was real, and it was connected to the galaxy's core. The team hypothesized they were seeing the wake of a runaway supermassive black hole, a black hole ejected from its galaxy, plowing through surrounding gas, compressing material ahead of it and leaving a trail of star formation behind. Skeptics offered alternative explanations. Perhaps it was a shredded dwarf galaxy, perhaps an edge-on disk seen at just the right angle. The evidence was suggestive but not conclusive. Then the James Webb Space Telescope provided the proof. Using its near-infrared spectrograph, the telescope did not just image the object, it measured motion. It analyzed how fast gas was moving at different points along the structure, and what it found removed all doubt. At the tip of the feature, there is a sharp velocity change. Gas suddenly jumps by roughly 600 kilometers per second over a distance of just 1 kiloparsec. This kind of abrupt kinematic discontinuity can only be caused by one thing: a supersonic bow shock. Something massive is pushing through the gas faster than sound waves can travel. It is compressing material in front of it, creating a shock front. Behind the shock, gas cools and collapses, forming new stars that stream out in a long tail. The black hole itself is invisible. Black holes do not emit light, but its effect on the surrounding environment screams its presence. The researchers calculated the black hole's velocity from the shock data, 954 kilometers per second, plus or minus about 100. This is nearly 1,000 kilometers per second, or roughly 2.2 million miles per hour. For perspective, Earth orbits its star at about 67,000 miles per hour. This black hole is moving 30 times faster. At this speed, the black hole will escape its galaxy entirely. It will never return. It will wander through intergalactic space forever, a cosmic exile. But how does something with the mass of 20 million stars get ejected from a galaxy? Two mechanisms can produce such enormous velocities. Both require extraordinary violence. The first involves a three-body interaction. If three supermassive black holes end up in the same galactic core, their gravitational dance can slingshot one member out at tremendous speed. The other two remain behind, bound in a shrinking orbit. The second involves gravitational waves. When two supermassive black holes merge, they release enormous energy in ripples through spacetime. If the merger is asymmetric, the burst of gravitational radiation can kick the newly formed black hole with enough force to escape. The team analyzing this runaway believes the merger scenario is most likely. The black hole's mass and velocity match predictions for a gravitational wave recoil kick. This discovery validates 50 years of theoretical work. Scientists predicted runaway supermassive black holes decades ago. Now, finally, we have seen one, and the galaxy left behind might have a strange future. A galaxy without a central supermassive black hole. We do not know what happens to such a system. We have never observed one. The runaway black hole did not come from nowhere. Its origin lies in a spectacular cosmic collision, two galaxies crashing together, their supermassive black holes spiraling toward each other, and the violent aftermath that sent one monster flying into the void. The host system is called the Cosmic Owl. It earned this name because of how it looks. Two ring galaxies approaching each other, their cores glowing brightly like a pair of eyes. The shape resembles an owl's face, staring back at observers across billions of light years. The Cosmic Owl lies roughly 8.8 billion light years away. At that distance, light takes nearly 9 billion years to reach us. We are seeing this system as it existed when the universe was less than 5 billion years old. Ring galaxies are already rare. They form when one galaxy punches through the center of another, sending ripples outward through the disk like a rock dropped in a pond. Finding two ring galaxies interacting with each other is extraordinary. But the Cosmic Owl contains something even more remarkable. That long linear feature extending from the system. The wake of the runaway supermassive black hole. Astronomers believe the sequence of events unfolded like this. Long ago, two separate galaxies existed. Each contained its own supermassive black hole. Perhaps they also contained additional black holes from previous mergers. These galaxies drifted closer together over millions of years, drawn by their mutual gravity. When galaxies collide, stars rarely hit other stars. Space is mostly empty, but the supermassive black holes at the galaxy centers sink toward each other. They orbit closer and closer, losing energy through gravitational interactions and eventually through gravitational wave radiation. In the Cosmic Owl system, something triggered an ejection. Either a three-body interaction flung one black hole outward, or two black holes merged asymmetrically, and the resulting recoil kick propelled the combined object away. The ejected black hole carried enormous momentum. It blasted through the surrounding gas at supersonic speed, compressing material ahead of it into a brilliant bow shock. Behind it, the compressed and cooling gas collapsed into new stars, creating a trail more than 60 kiloparsecs long. 60 kiloparsecs. That is roughly 200,000 light-years. For comparison, the entire Milky Way is only about 100,000 light-years across. The wake behind this runaway black hole is twice the diameter of our entire galaxy. The James Webb observations captured the bow shock in unprecedented detail. The spectrum revealed signatures of fast radiative shocks and rapid cooling. The chemistry and velocity measurements matched predictions for a supersonic object plowing through diffuse gas. Everything points to one conclusion. A supermassive black hole was violently ejected from the Cosmic Owl and is now racing through space, leaving creation in its wake. This discovery has profound implications. If runaway supermassive black holes are real, there might be many more wandering through the universe. Some estimates suggest millions could be drifting through intergalactic space, invisible and undetectable unless they happen to pass through gas clouds dense enough to produce visible effects. The universe may be haunted by cosmic exiles, monsters roaming the darkness between galaxies. But the cosmic owl also raises questions about how supermassive black holes form in the first place. If they can be ejected, merged, and flung across the universe, their history must be more violent and chaotic than we imagined. Understanding this violence requires understanding how black holes are born, and the answer might involve seeds far heavier than anyone expected. Where do supermassive black holes come from? This question has haunted astronomers for decades. We see black holes containing billions of solar masses sitting at the centers of galaxies. We find them existing less than 1 billion years after the Big Bang. But standard physics cannot explain how they grew so massive so quickly. Normal black holes form when massive stars die. A star, perhaps 30 times the mass of our star, exhausts its nuclear fuel, collapses, and leaves behind a black hole of maybe 10 to 30 solar masses. This is well understood, but 10 solar masses is nothing compared to 1 billion. If you started with a stellar mass black hole and fed it continuously at the maximum possible rate, it would take billions of years to reach supermassive scales. Longer than the universe had existed when we observe these ancient monsters. Something is missing from the story. Two main theories have emerged. The first proposes that early black holes grew through extreme feeding episodes. Perhaps the first stars were giants, hundreds of times more massive than typical modern stars. When they died, they left behind larger black holes. Perhaps those black holes merged repeatedly, combining their masses. Perhaps feeding rates occasionally exceeded the theoretical limits. This theory requires special conditions. It requires a continuous supply of gas, few disruptions, and enough time for cumulative growth. The math is tight, but possible. The second theory proposes something more dramatic. What if the first black holes did not start small? What if they were born massive? This is the heavy seeds theory. Instead of forming from dead stars, the first black holes might have formed directly from collapsing gas clouds. No star phase, no gradual growth from tiny beginning, just a direct gravitational implosion that created black holes 100,000 times more massive than our star in a single event. The conditions for direct collapse are extreme. You need an enormous gas cloud, relatively free of the heavy elements that would otherwise cool the gas and fragment it into smaller clumps. You need the cloud to collapse uniformly, without forming stars along the way. These conditions might have existed in the very early universe. Before the first generations of stars scattered heavy elements everywhere, pristine gas clouds could have remained metal-free and vulnerable to direct collapse. The James Webb Space Telescope has provided the first observational evidence supporting heavy seeds. A team from the Massachusetts Institute of Technology examined 6 ancient quasars, galaxies with actively feeding supermassive black holes, using the telescope's infrared instruments. They measured the light from stars surrounding these black holes, something impossible with previous telescopes because the black hole's glare overwhelmed everything else. The data revealed something significant. In these early systems, the black holes appear to have gained their mass before their host galaxies did. The stellar populations are younger and less developed than expected if galaxies and black holes grew together. This supports the heavy seeds scenario. If black holes started massive and galaxies assembled around them later, we would expect exactly this pattern. The black hole arrives first, already enormous. The galaxy catches up over billions of years. One researcher described it this way. In the early universe, supermassive black holes might have gained their mass before their host galaxies did. The initial black hole seeds could have been more massive than anything we observe today. The implications are staggering. Supermassive black holes might not be passengers in galactic evolution. They might be the foundations upon which galaxies are built. But heavy seeds are still theoretical. We have not directly observed one forming. The evidence is circumstantial, based on the properties of the systems we can see. To truly understand the birth of black holes, we need to look even further back. We need to witness the very first light. For hundreds of millions of years after the Big Bang, the universe was dark. Not just dark in the sense of empty space. Dark because light could not travel freely. The entire cosmos was filled with neutral hydrogen gas, and neutral hydrogen absorbs most wavelengths of energetic light. Any photon trying to cross the universe would be swallowed almost immediately. This period is called the Cosmic Dark Ages. No stars, no galaxies, just a vast fog of primordial gas, slowly cooling, waiting for something to change. Then the first stars ignited. Their intense ultraviolet radiation began ionizing the surrounding hydrogen, stripping electrons from atoms, creating pockets of transparent ionized gas where light could finally travel freely. These ionized regions grew, they expanded, they merged with neighboring bubbles. Slowly, the fog cleared, and the universe transitioned from opaque to transparent. This transformation is called the epoch of reionization. Understanding when it started, how it proceeded, and which sources were responsible has been one of the central goals of modern cosmology. For decades, scientists believed reionization did not begin until the universe was roughly 500 million years old. The first galaxies needed time to form and produce enough radiation to make a difference. Then, the James Webb Space Telescope found something that rewrote the timeline. A galaxy called JADESGSZ131 sits at a redshift, indicating we see it just 330 million years after the Big Bang. That is remarkably early, but what makes this galaxy extraordinary is not its age. It is what the galaxy is doing to its surroundings. When astronomers examined the spectrum of this galaxy, they found a signature they did not expect, a powerful emission line from ionized hydrogen. The signal was so strong that it shone with the brightness of 10 billion stellar masses. This light should not have been visible. At such early times, the neutral gas surrounding galaxies should have absorbed it completely, unless the galaxy had already carved out an ionized bubble around itself. That is exactly what the data show. This tiny, ancient galaxy had already begun clearing the cosmic fog just 330 million years after the Big Bang. The researchers who made this discovery described it as witnessing the onset of reionization at redshift 13. No one had predicted it would happen this early. The finding has immediate implications. If reionization started earlier than believed, the first stars and galaxies must have formed earlier too. The timeline of cosmic history needs revision, but questions remain. What is producing the radiation that ionized this bubble? The first stars are thought to be extremely hot and ultraviolet bright, but another possibility exists: supermassive black holes. When black holes consume gas, they generate enormous amounts of X-ray and ultraviolet radiation. A young, actively feeding black hole could ionize surrounding gas as effectively as millions of stars. The galaxy with the earliest ionized bubble might contain one of the first black holes. Scientists are investigating. Either way, this discovery marks a milestone. We have caught the universe in the act of waking up. The long, dark ages are ending. Light is beginning to win. But the transition was not simple. The reionization of the universe unfolded in ways far more complex than anyone imagined. The epoch of reionization was not a single event. It was a process that unfolded over hundreds of millions of years, across billions of light years, in ways that varied dramatically from region to region. Some parts of the universe lit up early, others remained dark for much longer. The cosmic fog did not lift uniformly. It cleared in patches, driven by local sources of radiation, shaped by the distribution of matter and the accidents of structure formation. Understanding this patchwork transformation has been one of the greatest challenges in cosmology. Until recently, we could barely observe it. The distances involved pushed the limits of every telescope. The signals were faint, absorbed, distorted by billions of years of cosmic expansion. The James Webb Space Telescope changed everything. With its infrared sensitivity and unprecedented resolution, the telescope can peer into the epoch of reionization and watch the process unfold. It can identify individual galaxies contributing to the ionizing radiation. It can map the boundaries between ionized bubbles and neutral fog. The emerging picture is both beautiful and chaotic. Reionization appears to have started much earlier than previously believed, perhaps around 300 million years after the Big Bang. But it did not complete until roughly 1.1 billion years after the Big Bang, more than 200 million years later than earlier estimates suggested. This extended timeline means the transformation was slow and uneven. Some galaxies were powerful enough to ionize their surroundings quickly. Others were weak, making little impact. The neutral regions between bubbles persisted stubbornly, resisting the advance of light. One major discovery involved extremely faint dwarf galaxies. For years, astronomers debated which sources were primarily responsible for reionization. Massive galaxies seemed like obvious candidates because they produced tremendous amounts of radiation. But there are not that many massive galaxies in the early universe. Dwarf galaxies, on the other hand, are everywhere. They are small, faint, and individually weak, but their numbers are overwhelming. When scientists analyzed the cumulative radiation from all the dwarf galaxies the telescope could detect, they found something surprising. These tiny galaxies produced enough ionizing photons to transform the entire universe. The team that made this discovery emphasized its significance. Ultra-faint galaxies played a crucial role in the early universe's evolution. They produced the radiation that changed neutral hydrogen into ionized plasma. Understanding low-mass galaxies is essential to understanding cosmic history. This conclusion has implications beyond reionization. If small galaxies dominated the photon budget of the early universe, they also dominated star formation. The majority of stars that have ever existed might have been born in galaxies too faint for us to see individually. The universe we observe, the bright galaxies and dramatic structures, might represent only the visible tip of a vast iceberg. Beneath the surface, countless tiny systems have shaped cosmic history from the beginning. But reionization is not just about counting photons. The process had physical consequences that echo to the present day. When ionizing radiation flooded through the universe, it heated the gas between galaxies. This heating changed how matter could collapse and form new structures. Small gas clouds that might have become dwarf galaxies were instead evaporated away. Reionization did not just illuminate the universe, it sculpted it. It determined which structures could form and which could not. We are still living with the consequences, and we are still debating exactly how it happened. They are almost invisible, scattered across the early universe, too faint for most telescopes to detect, small enough to fit inside a single arm of the Milky Way. Dwarf galaxies, the runts of the cosmic litter. For decades, astronomers overlooked them when thinking about the big questions. How did the universe evolve? What drove the major transitions in cosmic history? The focus was always on the giants, the massive galaxies with billions of stars, the dramatic quasars with supermassive black holes blazing at their centers. But the James Webb Space Telescope revealed an uncomfortable truth. The giants were never the whole story. Perhaps they were never even the most important part. The telescope examined 8 of the faintest dwarf galaxies ever detected during the epoch of reionization. These objects existed when the universe was still transitioning from darkness to light, roughly 900 million years after the Big Bang. Despite their small size, these galaxies were producing ionizing radiation at remarkable rates. Their combined output was enough to account for a significant fraction of the photons needed to transform the universe. And these 8 galaxies were just a tiny sample from a tiny patch of sky. When astronomers extrapolated to the full population of dwarf galaxies throughout the observable universe, the numbers became staggering. Faint dwarf galaxies might have produced the majority of the ionizing radiation during reionization. They might have done most of the work in clearing the cosmic fog. This discovery inverts our understanding of cosmic evolution. The smallest structures had the biggest impact. The physics makes sense in retrospect. Dwarf galaxies form first in the hierarchical model of structure formation. They are abundant because small clumps of matter collapse before large ones, and their stars, though fewer in number, can be extremely hot and luminous in the early universe. Massive galaxies form later through mergers of smaller systems. By the time they dominate the cosmic landscape, reionization is already complete. We were looking for the source of light in the wrong place. We focused on the brightest objects and missed the collective glow of countless dim ones. The lesson extends beyond astronomy. Sometimes the most significant changes come not from dramatic singular events, but from the accumulated effect of many small contributions. The universe teaches humility, but if dwarf galaxies drove reionization, we face a new challenge. These objects are extraordinarily difficult to study. Even the James Webb Space Telescope can only detect the brightest ones. The faintest members of the population remain invisible, their properties inferred rather than observed. Future telescopes may help. Larger mirrors, more sensitive instruments, and longer observation times could reveal the smallest galaxies in the early universe. Until then, we must work with incomplete data. The discovery also raises questions about what happened to these dwarf galaxies. We see their descendants in the local universe, small satellite galaxies orbiting larger ones like the Milky Way. But the numbers do not match perfectly. Some of the early dwarfs may have been destroyed, absorbed into larger galaxies, evaporated by the very radiation they helped produce. The universe that dwarf galaxies created might have turned against them. The ionizing light that ended the Dark Ages also heated intergalactic gas, preventing it from falling into small gravitational wells. Dwarf galaxies that formed before reionization could continue growing. Those that tried to form afterward found their fuel supply cut off. Reionization was not just a transition in visibility, it was a transformation of the conditions for cosmic structure formation, and its effects ripple forward through billions of years. The universe is expanding. This is not controversial. Since the 1920s, astronomers have known that distant galaxies are moving away from us. The farther away they are, the faster they recede. This expansion stretches space itself, carrying galaxies along like leaves on a flowing river. The rate of this expansion is measured by a number called the Hubble constant. Determining its precise value has been one of the central projects of modern cosmology, and it has led to one of the most frustrating puzzles in physics. There are two main ways to measure the Hubble constant. The first involves observing objects in the nearby universe. Astronomers identify stars with known intrinsic brightness, measure how bright they appear, and calculate their distance. By combining distances with recession velocities, they determine how fast space is expanding locally. The second method involves observing the cosmic microwave background, the afterglow of the Big Bang. This radiation carries information about the early universe. By analyzing its properties and applying the standard cosmological model, scientists can predict what the Hubble constant should be. These two methods should give the same answer. They do not. The nearby universe measurements consistently find expansion rates around 73 kilometers per second per megaparsec. The cosmic microwave background predictions give around 67 kilometers per second per megaparsec. The difference might seem small, but it is far larger than the measurement uncertainties allow. Both methods have been refined repeatedly over decades. The discrepancy persists. It even grows slightly as measurements improve. This disagreement is called the Hubble tension, and the James Webb Space Telescope just made it worse. Some astronomers hoped the tension was caused by measurement errors in the nearby universe observations. Previous telescopes, particularly the Hubble Space Telescope, struggled to resolve individual stars in distant galaxies. Perhaps blending of overlapping stars introduced systematic errors. The James Webb Space Telescope does not have this problem. Its resolution is dramatically sharper. It can cleanly separate stars that Hubble could not distinguish. When researchers reanalyzed the distance measurements using James Webb data, they found the previous results were correct. The expansion rate, measured in the nearby universe, remains around 73. The tension is real. This confirmation has profound implications. Either something is wrong with our measurements of the cosmic microwave background, or something is wrong with our cosmological model, or both. The standard model of cosmology, called lambda CDM, has explained observations successfully for decades. It describes a universe dominated by dark energy and cold dark matter, expanding according to Einstein's equations. It fits the cosmic microwave background beautifully, but it predicts a Hubble constant around 67. The universe appears to be expanding faster than this model allows. Something is missing. Cosmologists have proposed various solutions. Perhaps the early universe contained an additional component of energy that boosted expansion temporarily. Perhaps dark energy behaves differently than we assumed. Perhaps new physics is required. None of these proposals has gained universal acceptance. The tension remains unresolved, but one idea keeps appearing in discussions, a concept that might explain both the expansion problem and the puzzle of impossibly bright early galaxies. Early dark energy. What if two of cosmology's biggest puzzles have the same solution? The first puzzle is the Hubble tension. The universe expands faster than our standard model predicts. The second puzzle involves the early galaxies found by the James Webb Space Telescope. They are too massive and too luminous for their age. Standard models cannot explain how they grew so quickly. These puzzles seemed unrelated. One involves the expansion rate of space. The other involves the formation of structure within space. Different phenomena governed by different physics. But a team of physicists from the Massachusetts Institute of Technology realized the connection. They proposed that both anomalies could be explained by early dark energy. Dark energy is the name we give to whatever is accelerating the universe's expansion today. In the standard model, dark energy has a constant density throughout cosmic history. It does not change. It does not interact with matter in complex ways. But what if there was additional dark energy in the early universe? A temporary component that existed only during the first few 100 million years, then faded away. This early dark energy would have pushed the universe apart faster during its infancy. It would have stretched space more quickly than the standard model assumes. This accelerated early expansion would have several effects. It would change the balance of cosmological parameters. The seeds of structure formation would be slightly larger. Dark matter halos would grow faster. Galaxies would form earlier and brighter. The team tested this idea using sophisticated simulations. They incorporated a model of early dark energy that had been proposed to resolve the Hubble tension and asked what it would do to galaxy formation. The results were striking. With early dark energy, the skeletal structure of the early universe changes in subtle but important ways. The amplitude of density fluctuations increases. Dark matter halos become bigger. Galaxies form earlier and shine more brightly. The model predicted exactly what the James Webb Space Telescope observed: bright, massive galaxies appearing much sooner than standard cosmology allows. One researcher described the finding this way: "We demonstrated the potential of early dark energy as a unified solution to two major issues facing cosmology. This might be evidence for its existence if the observational findings from the telescope continue to hold. The proposal is elegant. A single modification to cosmology could resolve two separate puzzles. This is how physics often progresses. Unexplained phenomena accumulate until someone identifies the deeper principle that connects them. But early dark energy remains controversial. Not all physicists are convinced. Some argue the evidence is circumstantial. Others point out that early dark energy creates tensions with other observations. The debate continues. More data are needed. The James Webb Space Telescope keeps observing, adding to the evidence on both sides. What seems increasingly clear is that our understanding of the universe is incomplete. The standard model has served us well for decades, but It may be reaching its limits. The anomalies are multiplying faster than explanations. And another mystery is emerging from the data, something even stranger than the Hubble tension. Dark energy itself might be changing. Dark energy was supposed to be constant. The cosmological constant, first proposed by Einstein and later revived to explain the accelerating expansion of the universe, was assumed to have the same strength everywhere and at all times, a fixed value woven into the fabric of space itself. This assumption made the math tractable. It allowed cosmologists to build predictive models. It worked well for decades. But new observations suggest dark energy might not be constant after all. Data from multiple surveys, including the Dark Energy Spectroscopic Instrument, and analyses incorporating James Webb Space Telescope observations, hint that dark energy has weakened over the past 4 to 5 billion years. If true, this discovery would overturn one of the foundational assumptions of modern cosmology. The evidence comes from measuring the expansion history of the universe with unprecedented precision. By observing how galaxies cluster at different distances, astronomers can reconstruct how fast space expanded at various epochs. The results show a curious pattern. The expansion rate in the distant past matches predictions reasonably well. But in the more recent universe, something seems off. The expansion is not accelerating as uniformly as the constant dark energy model predicts. One interpretation is that dark energy had greater strength in the past and has been gradually declining. The universe's acceleration is slowing down. The implications are profound. If dark energy continues to weaken, the accelerating expansion could eventually stop. The universe might coast to a halt, or, depending on how dark energy evolves, expansion could even reverse. Some researchers speculate about extreme scenarios. A weakening dark energy could lead to a big crunch, where the universe collapses back on itself. Or it could transition to a big rip, where the decay of dark energy leads to increasingly violent expansion that eventually tears apart galaxies, stars, and atoms. These scenarios are speculative. The current data show only hints of variation, not definitive proof. The uncertainties are large. More observations are needed. But the mere possibility that dark energy is not constant represents a fundamental shift in cosmological thinking. For decades, physicists assumed the universe had a fixed accelerator pedal. Dark energy pushed expansion faster and faster forever. The ultimate fate of the cosmos was isolation, as galaxies receded beyond each other's horizons into eternal darkness. A variable dark energy changes this picture completely. The future becomes uncertain in ways it never was before. The James Webb Space Telescope contributes to this story indirectly. Its observations of unexpectedly mature galaxies in the early universe challenge timelines that assume constant dark energy. If dark energy was stronger or behaved differently in the early cosmos, it could explain some of the anomalies. Everything connects. The Hubble tension, the massive early galaxies, the variable dark energy. These are not separate puzzles. They are facets of a single, deeper mystery about the nature of space, time, and energy. Cosmology is entering a period of upheaval. The certainties of the past are dissolving. New physics lurks just beyond our current understanding, and the telescope keeps finding things that should not exist. Sometimes, the universe hides its most dangerous objects in plain sight. A galaxy known as Virgil appeared completely ordinary when astronomers first observed it. Sitting in the early universe, roughly 800 million years after the Big Bang, it looked like a typical young galaxy quietly forming stars. Its ultraviolet and optical light showed nothing unusual. Then, the James Webb Space Telescope revealed its true nature. Using the mid-infrared instrument, researchers penetrated deeper into the galaxy's emission than any previous telescope could reach. What they found transformed Virgil from mundane to extraordinary. Beneath its calm exterior lurked an active supermassive black hole, a monster hidden behind veils of dust and gas. The optical light showed only the galaxy's public face. The infrared light exposed its violent heart. One researcher described Virgil as having two personalities. Its ultraviolet and optical appearance showed the good side, a typical young galaxy, quietly forming stars. Its infrared emission revealed something far more extreme. This discovery has implications beyond a single galaxy. The James Webb Telescope's surveys often obtain deep imaging with near-infrared cameras, but only brief observations with mid-infrared instruments. The longer wavelengths require much more observation time to achieve the same sensitivity. This means astronomers might be systematically missing a hidden population of dust-obscured black holes, objects that look normal at shorter wavelengths but harbor monsters at their cores. If Virgil is not unique, and statistically, it probably is not, then the early universe contained many more active black holes than current surveys suggest. These hidden giants could have played significant roles in cosmic history. They might have contributed to reionization, flooding the early universe with ionizing radiation from behind their dusty shrouds. They might explain some of the excess brightness seen in early galaxies. They might be the missing link between black hole seeds and the supermassive black holes we see today. The discovery also demonstrates the power of multi-wavelength observation. No single type of light tells the whole story. The universe looks different in ultraviolet, visible, infrared, and radio wavelengths. Each window reveals different phenomena. Before the James Webb Space Telescope, our infrared window on the distant universe was narrow and blurry. Now it is wide open, and what we see is reshaping our understanding of cosmic evolution. Virgil sits at a crucial moment in cosmic history. The universe was still clearing its primordial fog. The first major structures were assembling. Black holes were growing rapidly, consuming gas and influencing their surroundings. Understanding objects like Virgil helps us understand this transformative epoch. Every hidden black hole we find adds to the picture. Every seemingly ordinary galaxy that reveals an extraordinary secret teaches us something new. The universe is full of disguised monsters. They hide behind dust and distance, appearing innocent until the right instrument unmasks them. And Virgil is not the only surprise hiding in the data. The most distant galaxy ever discovered also held secrets that challenged everything astronomers thought they knew about the chemistry of the early universe. The most distant galaxy ever discovered should have been primitive. At a redshift of 14.3, we see this object as it existed just 290 million years after the Big Bang. The universe at that moment was a cosmic infant. The first stars had barely ignited. The first heavy elements were only beginning to form. Scientists expected to find a chaotic, metal-poor system, a jumble of hydrogen and helium, with perhaps trace amounts of heavier elements, something rough and unfinished, appropriate for the dawn of cosmic structure. Instead, the James Webb Space Telescope found oxygen, significant amounts of oxygen, enough to indicate that multiple generations of stars had already lived and died within this ancient galaxy. Enough to suggest that star formation began even earlier than anyone believed possible. This discovery requires careful explanation because its implications are staggering. Oxygen does not exist at the beginning of the universe. The Big Bang produced only the lightest elements. Hydrogen made up about 75% of primordial matter. Helium made up most of the rest. Trace amounts of lithium completed the inventory. Everything else, every element heavier than lithium, was forged inside stars. When stars burn hydrogen into helium, they release energy. When they burn helium into carbon, they release more energy. The process continues, building heavier and heavier elements until the star runs out of fuel. Massive stars end their lives in supernova explosions. These explosions scatter the heavy elements into space, seeding the gas clouds that will form the next generation of stars. Over billions of years, this cosmic recycling enriches the universe with the full periodic table of elements. Oxygen requires this process. It forms in the cores of massive stars and spreads through supernovae. Finding oxygen in a galaxy means stars have already lived and died there. The galaxy at redshift 14.3 contains enough oxygen to indicate substantial stellar processing. This is not a trace detection. The mid-infrared instrument aboard the telescope measured clear signatures of oxygen emission. The team that made this discovery used extraordinary resources. They devoted approximately 9 days of telescope time to this single object, 167 hours of near-infrared imaging, 43 hours of mid-infrared imaging, all focused on a patch of sky so small it would be covered by a grain of sand held at arm's length. They were lucky. The galaxy happened to sit in exactly the right position to be observable with the mid-infrared instrument. A fraction of a degree in any direction would have missed it. What they found challenges the timeline of cosmic chemical evolution. If this galaxy already contains significant oxygen just 290 million years after the Big Bang, then the first stars must have formed, lived, and died even earlier. Current models suggest the first stars ignited somewhere between 50 and 100 million years after the Big Bang. But those were supposed to be isolated objects, rare pioneers in a mostly empty universe. The oxygen abundance in this distant galaxy suggests star formation was already widespread and prolific. The universe was not slowly waking up. It was racing to maturity from the very beginning. One researcher described the finding as totally unexpected. The complex chemical composition, so early in cosmic history, forces revisions to models of galaxy formation. Whatever processes built this galaxy operated far faster than anyone anticipated. But chemistry is not the only surprise hiding in the early universe. The telescope has also witnessed violence on a cosmic scale, the explosive death of a massive star, captured in unprecedented detail, from an era when such events were thought to be rare. The first supernova at cosmic dawn, on March 14, 2025, a burst of high-energy radiation reached Earth. It came from impossibly far away, a gamma-ray burst, one of the most violent events in the universe, originating from a time when the cosmos was only 730 million years old. Gamma-ray bursts occur when massive stars die, not ordinary deaths, but catastrophic collapses that form black holes or neutron stars. The infalling material releases tremendous energy, focused into narrow jets that punch through the dying star and blast into space. These events are so bright, they can be seen across the entire observable universe. They serve as cosmic beacons, marking the deaths of the most massive stars in existence. When astronomers detected this particular burst, they immediately recognized its significance. The redshift indicated extreme distance. This was one of the earliest stellar deaths ever witnessed. But detecting the gamma-ray burst was only the beginning. The real prize would be observing what came after, the supernova. Gamma-ray bursts are associated with a specific type of supernova called a hypernova, or broad-lined type IC supernova. These explosions occur when massive stars that have lost their outer hydrogen layers collapse and explode. The connection between gamma-ray bursts and supernovae was established through observations in the local universe. But no one had ever confirmed this connection at such extreme cosmic distances. The early universe was supposed to be different. Stars formed from pristine gas. Their deaths might have followed unfamiliar patterns. 110 days after the initial burst, the James Webb Space Telescope pointed at the location. Using its near-infrared camera, astronomers separated the fading light of the explosion from the dim glow of its host galaxy. They found a supernova. The brightness and spectral features closely match supernovae associated with gamma-ray bursts in the local universe. The physics appeared identical. Massive stars in the early cosmos died the same way massive stars die today. This confirmation carries profound implications. It means the fundamental processes of stellar death were already established when the universe was only 5% of its current age. The physics did not need billions of years to settle into familiar patterns. It was consistent from nearly the beginning. One researcher involved in the discovery described it as a smoking gun. The observation connects the deaths of massive stars with gamma-ray bursts across cosmic time. It demonstrates that the cycle of stellar birth, life, and explosive death was operating at cosmic dawn. But the finding also raises questions. Supernovae scatter heavy elements into space, seeding future generations of stars with the materials needed to form planets and potentially life. If supernovae were already common 730 million years after the Big Bang, the chemical enrichment of the universe was well underway. This connects to the oxygen detected in the most distant galaxy. The supernovae that spread that oxygen must have occurred even earlier. The first generations of stars were not just forming, they were already dying in spectacular fashion. The early universe was a violent place. Stars ignited rapidly, burned through their fuel in millions of years, and exploded. Their deaths fertilized the cosmos, preparing it for the complex chemistry that would eventually produce planets, oceans, and life. Speaking of planets, the James Webb Space Telescope has revealed worlds stranger than anything in our own cosmic neighborhood, including one that might rain diamonds from skies of pure carbon. What happens when a planet orbits a dead star? Not just any dead star, a pulsar, a neutron star spinning dozens of times per second, beaming radiation across space like a cosmic lighthouse. An object with the mass of our star compressed into a sphere the size of a city. The answer, it turns out, is something no one predicted. The James Webb Space Telescope has discovered a planet unlike anything ever observed. Its atmosphere defies every known formation mechanism. Its composition challenges our understanding of planetary science. And deep within its interior, diamonds might be forming continuously. The planet orbits a pulsar roughly 6,000 light-years away. It has a mass comparable to Jupiter, making it a gas giant by any definition. But its atmosphere contains no water, no methane, no carbon dioxide, none of the familiar molecules we find in gas giants throughout our galaxy. Instead, its atmosphere is dominated by helium and molecular carbon. Pure carbon, in forms designated C2 and C3 by chemists. These molecules are extremely unusual because, at planetary temperatures, carbon normally bonds with other elements. Finding pure carbon suggests an environment entirely unlike anything in our cosmic neighborhood. One researcher described the discovery as an absolute surprise. The collective reaction was disbelief. This is extremely different from what anyone expected. The planet is also misshapen. Gravitational forces from the nearby pulsar stretch it into a lemon shape. It completes a full orbit in under 8 hours, racing around its dead stellar companion at tremendous speed. The intense pressure inside the planet could cause remarkable transformations. Carbon, under extreme compression, crystallizes. And crystallized carbon is diamond. Scientists believe the carbon in this planet's atmosphere could be sinking into the interior, where crushing pressures transform it into diamond crystals. These diamonds would fall like rain, accumulating somewhere in the planet's depths. Diamond rain is not entirely new to planetary science. Researchers have theorized it might occur deep inside Neptune and Uranus in our own cosmic neighborhood. But this distant world takes the concept to extremes. The mystery deepens when scientists try to explain how such a planet formed. Normal planets form from the disk of gas and dust surrounding young stars. They inherit the chemical composition of their birth cloud, which typically contains abundant hydrogen, oxygen, nitrogen, and other common elements. A planet with pure carbon and helium cannot have formed this way. Pulsar planets are rare to begin with. Only a handful are known. They might form from the debris of the supernova that created the pulsar, or from materials stripped from a companion star, but neither scenario easily produces the observed composition. One proposed explanation involves crystallization processes unique to cooling compact objects. As the interior cooled over billions of years, carbon and oxygen separated. Pure carbon crystals floated to the top and mixed into the helium atmosphere. The oxygen and nitrogen somehow stayed behind. The physics is speculative. No one fully understands this world. What seems clear is that planetary diversity extends far beyond our imagination. The universe creates worlds we never conceived of. Gas giants with diamond interiors, lemon-shaped planets racing around stellar corpses, atmospheres of pure carbon under alien skies. But strange planets are not limited to exotic systems around dead stars. The telescope has found bizarre worlds much closer to home, including one that should have been stripped bare but somehow kept its atmosphere. Some planets should not have atmospheres. When a world orbits extremely close to its star, the intense radiation strips away any gases clinging to its surface. The stellar wind blasts particles into space. Ultraviolet light breaks molecular bonds. Over millions of years, the atmosphere evaporates completely, leaving bare rock behind. This is well-established physics. Countless examples confirm it. Small planets close to their stars are airless. Then the James Webb Space Telescope examined a planet called TOI 561b. This world orbits one of the oldest stars in the Milky Way. The star formed roughly 10 billion years ago, when the universe was less than 4 billion years old. Any planets in this system have endured unimaginable spans of time. TOI 561b orbits so close that its year lasts less than 12 hours. At that distance, the dayside temperature exceeds 2,000 degrees. The surface is molten. A global ocean of magma covers the planet, glowing orange and red under perpetual stellar bombardment. By every expectation, this world should be bare rock. 10 billion years of intense radiation should have stripped away any atmosphere long ago. The planet should be a scorched cinder, its original gases scattered across space. But when astronomers measured the planet's temperature, something was wrong. The dayside was cooler than predicted. Heat was being distributed away from the stellar-facing hemisphere somehow. Something was transporting energy. The only explanation is an atmosphere. Further analysis confirmed the presence of a thick blanket of gases above the magma ocean, not a thin wisp of rock vapor, a substantial atmosphere rich in volatile compounds. This is the strongest evidence yet for an atmosphere on a rocky planet outside our cosmic neighborhood, and it exists where no atmosphere should survive. One researcher described the planet as really like a wet lava ball. The atmosphere somehow persists despite conditions that should have destroyed it. How is this possible? The leading theory involves continuous replenishment. The magma ocean constantly releases gases. Volcanic activity on a planetary scale pumps volatiles into the atmosphere faster than stellar radiation can strip them away. This creates a dynamic equilibrium. The atmosphere is constantly being destroyed and constantly being rebuilt. It exists in a state of perpetual regeneration. The implications extend beyond this single world. If magma oceans can sustain atmospheres even under extreme stellar bombardment, then the range of potentially interesting planets expands dramatically. Worlds we dismissed as airless might actually maintain thin but significant gas envelopes. This matters for the search for life. Atmospheres regulate temperature. They shield surfaces from radiation. They enable complex chemistry. A universe with more atmospheric planets is a universe with more possibilities. But TOI 561b is not habitable. Its temperatures far exceed anything compatible with life as we know it. The interest here is scientific, not astrobiological. For hints of life, astronomers look elsewhere, to a world that has sparked fierce debate about what the telescope can actually detect, a planet where possible biosignatures have ignited controversy across the scientific community. Can the James Webb Space Telescope detect signs of life on distant worlds? This question has divided astronomers since the telescope began operations. The answer depends not just on the telescope's capabilities, but on what we mean by life and how confidently we can interpret chemical signatures across interstellar distances. In early 2025, a team of researchers made a dramatic announcement. They had found what they called the strongest evidence yet for potential biosignature gases in the atmosphere of an exoplanet named K218b. The The planet orbits a red dwarf star roughly 124 light-years away. It is larger than Earth but smaller than Neptune, placing it in a category called sub-Neptunes. These worlds have no analogue in our own cosmic neighborhood, making them particularly mysterious. K218b sits in its star's habitable zone, where temperatures might allow liquid water to exist. Some researchers have proposed it could be a Haitian world, a planet covered by a global ocean beneath a thick hydrogen-rich atmosphere. Using new transit spectra from the James Webb Space Telescope, the team announced they had detected signatures consistent with dimethyl sulfide and possibly dimethyl disulfide. On Earth, these gases are strongly associated with marine biology. Phytoplankton produce them in our oceans. The implication was electrifying. If these gases exist on K218b, and if they cannot be produced by non-biological processes, they might indicate life. But the scientific community responded with intense skepticism. Other researchers argued the signal was too weak to draw definitive conclusions. The data were noisy. The detection was at the edge of what the telescope could measure. Alternative explanations could not be ruled out. Critics also questioned the Haitian world concept itself. Some argued K218b might not be an ocean world at all, but a mini Neptune with a thick atmosphere and no solid surface. Under those conditions, any biosignature interpretation would be meaningless. The debate highlighted the limits of current technology. The James Webb Space Telescope was not designed specifically for exoplanet atmospheres. It was conceived before the explosion of exoplanet discoveries. Now, scientists are pushing it beyond its original specifications, extracting signals from the noise at the very edge of possibility. More observations are planned. Additional transits have been captured and await analysis. The data might eventually clarify whether dimethyl sulfide truly exists on K218b. But even if the detection is confirmed, proving biological origin will be extraordinarily difficult. We would need to demonstrate that no abiotic process could produce these gases. Given how little we know about exotic planetary chemistry, that bar may be impossible to clear with current knowledge. Some astronomers see value in the controversy regardless of outcome. If the result is that the public becomes more cautious about future claims of life detection, that would not be a terrible thing. Science requires skepticism. K218b remains a high-value target for understanding sub-Neptune atmospheres. Whether or not it hosts life, studying its chemistry teaches us about planetary diversity and the range of conditions that exist in our galaxy. The search for life continues. Each observation brings us closer to answering the oldest question humans have asked: are we alone? But before we can answer that question, we must understand the environments where life might emerge. And the early universe held surprises that pushed the boundaries of what stars can be. What did the first stars look like? This question has haunted astronomers for decades. The first generation of stars, called population 3 stars, formed from pristine gas containing only hydrogen and helium. They had no heavy elements to cool the gas efficiently, so they collapsed into enormous masses. Theory predicts they were giants, perhaps hundreds of times more massive than typical modern stars. These primordial titans would have burned hot and bright, flooding the early universe with ultraviolet radiation. They would have lived fast and died young, exploding as supernovae that seeded the cosmos with the first heavy elements. But no one has ever seen a population 3 star directly. They existed too early, too briefly, and too far away. By the time their light reaches us, they have long since died. The closest we can get is finding environments similar to the primordial conditions. Galaxies with extremely low metal content, where star formation might follow ancient patterns. The James Webb Space Telescope has found such a place. A galaxy called XL 63107 sits at a redshift indicating we see it less than 600 million years after the Big Bang. It is tiny, measuring less than 200 light-years across. For comparison, the Milky Way spans 100,000 light-years. But what makes this galaxy extraordinary is its chemistry. It contains only 1.6% of the oxygen found in our star. This is among the lowest metallicity ever measured in any galaxy at any distance, and its stars appear strange. The spectrum shows signatures that do not quite fit standard models. The ionization levels are unusually high. The radiation is unusually intense. Something is producing enormous amounts of energetic photons. One interpretation is that this galaxy contains a top-heavy initial mass function. This means massive stars are more common than they should be. Instead of the normal distribution of stellar masses, this ancient system is weighted toward giants. If true, this has enormous implications for understanding reionization. Massive stars produce far more ionizing radiation per unit mass than small stars. A universe where early galaxies had top-heavy mass functions would have reionized much faster than one with normal stellar populations. Another possibility is even more exciting. Perhaps the conditions in Excel's 63107 are so similar to primordial environments that it hosts stars resembling population 3 objects. Not the true first generation, which would contain zero metals, but something close, a window into what the earliest stellar populations might have been like. The galaxy is forming stars at a remarkable rate given its tiny size, roughly 8 times the mass of our star every year, packed into a volume smaller than most star clusters. The intensity of this activity produces the unusual blue light detected in images. Scientists emphasize that more observations are needed. The interpretations are preliminary, but the discovery demonstrates that extremely primitive galaxies existed during the cosmic dawn, and the telescope can study them in detail. We are approaching the boundary of first light, the very first structures to emerge from the darkness. Each metal-poor galaxy brings us closer to understanding how the universe transitioned from primordial simplicity to the complex, enriched state we see today. But not all early galaxies were actively forming stars. Some had already stopped, and their premature dormancy creates another puzzle for cosmology. Galaxies are supposed to evolve slowly. The standard picture goes like this. Young galaxies form stars vigorously. Gas flows in, collapses, ignites. Over billions of years, the gas supply gradually depletes. Star formation slows. Eventually, the galaxy becomes quiescent, a red and dead system containing only old stars. This process should take many billions of years. A galaxy forming in the early universe should remain active for a long time before exhausting its fuel. The James Webb Space Telescope found galaxies that broke this rule. Deep in the early universe, less than 2 billion years after the Big Bang, astronomers discovered galaxies that had already stopped forming stars. They were dormant, quiescent. Their stellar populations showed ages indicating star formation had ceased hundreds of millions of years earlier. These galaxies were not supposed to exist. Scientists nicknamed them sleeping beauties, systems that fell into cosmic slumber far earlier than any model predicted. Their existence challenges our understanding of how galaxies evolve. The puzzle has 2 parts. First, these galaxies must have formed their stars extraordinarily quickly. To be quiescent by 2 billion years after the Big Bang, they needed to produce all their stellar mass within the first billion years. That is an astonishing rate of star formation. Second, something must have turned off that star formation abruptly. Gas supply must have been cut. Whether through consumption, expulsion, or some other mechanism, the fuel vanished. Several explanations have been proposed. Active galactic nuclei might be responsible. If a supermassive black hole at the center of a galaxy becomes extremely active, its radiation can heat surrounding gas and prevent it from collapsing into stars. The black hole effectively sterilizes its host galaxy, shutting down star formation through sheer energetic output. Galaxy mergers might also play a role. When galaxies collide, the resulting chaos can trigger intense bursts of star formation that consume available gas rapidly. The merger remnant then sits quietly, depleted of fuel. Environmental effects could contribute as well. Galaxies in dense regions of the universe experience different conditions than isolated systems. gas might be stripped away by interactions with neighboring structures. But none of these explanations fully accounts for the observed population. The sleeping beauties are too numerous, too massive, and too early for any single mechanism to explain. The discovery adds to the growing evidence that the early universe was more dynamic than standard models predict. Galaxies formed faster. They evolved faster. They reached endpoints that should have taken billions of additional years. Something accelerated cosmic evolution, whether it was early dark energy, different dark matter properties, or physics we have not yet identified. The universe moved quickly from its primordial state to conditions resembling the modern cosmos. The sleeping beauties are symptoms of this accelerated timeline. They demonstrate that galaxy evolution was already advanced when the universe was a fraction of its current age. And they are not the only evidence of premature cosmic maturity. Spiral galaxies, those icons of organized structure, also appeared far too soon. Spiral galaxies are the crown jewels of cosmic structure. Their sweeping arms, elegant symmetry, and dynamic rotation represent billions of years of gravitational choreography. They are mature systems, products of extended evolution and stable conditions. Our own galaxy is a spiral. From our position within it, we see the band of light called the Milky Way stretching across the night sky. That band is the disk of our galaxy seen edge-on, packed with hundreds of billions of stars organized into graceful spiral patterns. Creating such structure requires time. Dark matter must accumulate into halos. Gas must settle into rotating disks. Density waves must propagate, triggering star formation along curved paths. The process unfolds over many billions of years. At least, that was the assumption. In early 2025, the James Webb Space Telescope delivered a discovery that challenged this understanding. A massive spiral galaxy, nicknamed the Big Wheel, existed within the first 2 billion years of the universe. The galaxy should have been elliptical. Massive early galaxies were expected to be smooth blobs of stars, their structures not yet organized into disks and arms. The violent mergers, thought to dominate early galaxy growth, should have prevented spiral formation. But the Big Wheel has clear spiral structure. Its arms are well defined. Its rotation is orderly. It looks like a galaxy from the local universe, not from the cosmic dawn. One researcher described the finding as remarkable. Having such a beautiful spiral structure means whatever processes built this galaxy happened in a very neat way. Either violent mergers did not occur, or most of the mass formed in place without major disruptions. The discovery joins a growing list of unexpectedly mature early structures. The spiral galaxy, Alaknanda, the numerous disk galaxies found at high redshift, the sleeping beauties with their already old stellar populations. A pattern is emerging. The early universe was not the chaotic, primitive environment we expected. It was capable of producing organized, sophisticated structures far sooner than models predict. This challenges fundamental aspects of cosmological theory. The hierarchical model of structure formation assumes small things form first and merge into big things over time. Smooth, organized structures should be late arrivals, products of extended peaceful evolution. But the observations show the opposite. Some of the largest, most organized structures appeared early. They beat the predicted timeline by billions of years. The implications ripple through every aspect of astronomy. Galaxy formation models need revision. Dark matter simulations need new parameters. The basic narrative of cosmic evolution needs updating. Some researchers suggest early dark energy might explain the accelerated structure formation. Others propose modified dark matter properties. Still others wonder if we are missing fundamental physics. No consensus has emerged. The debate continues. Each new observation from the James Webb Space Telescope adds evidence and complexity. What seems increasingly clear is that our picture of the universe is incomplete. The telescope has not just filled in details. It has revealed that the entire framework needs reconsidering. And so we arrive at the most unsettling conclusion of all. Everything we believed is being questioned. The timeline of cosmic evolution, the formation of galaxies and black holes, the nature of dark energy, the rate of cosmic expansion. The models that served astronomy for decades are failing to explain what the most powerful telescope ever built actually sees. This is not a minor adjustment. This is a fundamental reassessment. Consider what the James Webb Space Telescope has revealed in just a few years of operation. Galaxies appearing too early, too massive, too organized. Spiral structures existing billions of years before they should. Sleeping systems that stopped forming stars when the universe was still young. Black holes too large for their host galaxies. Objects feeding at impossible rates. A runaway supermassive black hole tearing through space at 2 million miles per hour, validating 50 years of theory with a single dramatic observation. Little red dots scattered across the early cosmos, now understood to be young black holes wrapped in gas cocoons. Perhaps an entirely new class of object called black hole stars. The seeds of the supermassive monsters that anchor every major galaxy. The epoch of reionization starting earlier than believed. Faint dwarf galaxies producing enough radiation to transform the entire universe. The first ionized bubbles appearing just 330 million years after the Big Bang. The Hubble tension confirmed and deepened. The universe expanding faster than our best model predicts. Dark energy possibly weakening over time, throwing the ultimate fate of the cosmos into question. Exoplanets defying expectations. Lava worlds with atmospheres that should not exist. Lemon-shaped planets with diamond rain around dead stars. Potential biosignatures sparking fierce debate about whether we can detect life from light years away. Each discovery individually would be significant. Together, they constitute a revolution. Science advances through exactly this process. Observations challenge theories. Theories are revised or replaced. Understanding deepens. The cycle continues. But the current moment feels different. The anomalies are not isolated. They appear everywhere the telescope looks. Early galaxies, black holes, expansion rates, dark energy. The problems span multiple fields and point towards something missing from our fundamental picture. Some researchers believe early dark energy might unify several puzzles. Others propose modifications to dark matter. Still others wonder if general relativity itself needs revision on cosmological scales. No one knows yet. The data are still coming in. The James Webb Space Telescope continues observing, adding new discoveries weekly. Future telescopes will extend these findings, probing even deeper into cosmic history. What we can say with confidence is this: the universe is stranger and more dynamic than we imagined. It evolved faster. It created structure more efficiently. It harbors objects and phenomena that humble our theories. And this should excite us, not discourage us. The greatest moments in science come when observations outrun explanation, when nature reveals itself to be richer than our models captured, when we must return to first principles and think again. We are living through such a moment. The telescope 1 million miles from Earth has shattered our comfortable assumptions. The cosmos is not what we thought, but now we know what questions to ask. We know where the mysteries lie. We have clues pointing toward deeper truths. The journey of discovery continues, and whatever we find next will be stranger still. Some images define an era. In 1995, the Hubble Space Telescope captured a photograph that became one of the most famous scientific images ever taken. Towering columns of gas and dust, backlit by the glow of newborn stars, rising like cathedral spires against the darkness of space. The pillars of creation. For nearly 3 decades, this image shaped how humanity visualized cosmic birth. Countless textbooks reproduced it. Museum visitors stood transfixed before enormous prints. The pillars became synonymous with the wonder of space exploration. Then the James Webb Space Telescope looked again, and what it revealed transformed our understanding of what happens inside those majestic towers. The pillars sit within the Eagle Nebula, roughly 6,500 light-years from Earth. Each column stretches several light-years tall. For scale, the distance from our star to the nearest other star is just over 4 light-years. These are structures of almost incomprehensible size. Hubble showed us their beauty. Webb showed us their violence. In near-infrared light, the telescope pierced the dusty exteriors that had hidden the pillars' interiors from view. Suddenly, astronomers could see deep inside the columns, and what they found was chaos. Newborn stars by the hundreds, fiery jets blasting outward at supersonic speeds, shock waves rippling through the gas. The pillars are not peaceful nurseries. They are battlegrounds where gravity wages war against radiation, and new stars claw their way into existence. A research team studying the Webb data identified 253 young stellar object candidates within the pillars. These are protostars, objects still gathering mass from their surroundings, some only a few 100,000 years old, cosmic infants by any measure. But the most striking finding was where these infant stars cluster. They concentrate along the edges of the pillars, not randomly distributed throughout, and their ages appear to decrease with distance from the massive stars, illuminating the nebula. This pattern tells a story. The intense radiation from nearby mature stars is sculpting the pillars, eroding them like wind-carving sandstone formations in a desert. But as the radiation compresses the gas at the pillar edges, it also triggers gravitational collapse. The pillars are being destroyed, and their destruction is creating new stars. This process, called triggered star formation, had been theorized for decades, but never observed so clearly. The Webb data show it happening in real time. Star formation rates within the pillars have increased dramatically over the past million years, precisely as the erosion intensified. The wavy patterns along the pillar edges that look like glowing lava flows are not decoration. They are the supersonic jets from newborn stars smashing into the surrounding gas. Each collision creates bow shocks, rippling patterns of heated material that trace the violence of stellar birth. One researcher described the images as practically pulsing with activity. These young stars, perhaps only a few 100,000 years old, are announcing their arrival with spectacular violence. But there is tragedy hidden in this beauty. The same radiation triggering new star formation is also dooming the pillars themselves. Eventually, the columns will be completely eroded away. Their constituent gas will disperse into space. The stars they spawned will drift apart. The pillars of creation are temporary structures, monuments to a moment in cosmic evolution that will pass. In perhaps 100,000 years, they will be gone entirely. We are fortunate to witness them while they still stand. And yet, while we study stellar nurseries in our own galaxy, the telescope has also turned its attention to mysteries much closer to home, including the most distant planet in our cosmic neighborhood, where light dances in ways no one expected. For 30 years, astronomers searched. They knew auroras should exist on Neptune. Every other giant planet displayed them. Jupiter's auroras blaze hundreds of times brighter than Earth's. Saturn wears luminous halos around its poles. Even distant Uranus glows with faint northern and southern lights. But Neptune refused to reveal its secret. When Voyager 2 flew past the ice giant in 1989, instruments detected tantalizing hints of auroral activity, but the technology of that era could not confirm or characterize what was happening in Neptune's upper atmosphere. Ground-based telescopes tried for decades afterward. The Keck Observatory in Hawaii pointed its massive mirrors at the distant world. The Very Large Telescope in Chile searched through the infrared. Nothing definitive emerged. The problem was distance. Neptune orbits 30 times farther from our star than Earth does. At such vast separation, the faint glow of an aurora is extremely difficult to detect against the overwhelming blackness of space. Then the James Webb Space Telescope took its turn. In June of 2023, astronomers directed the telescope's near-infrared spectrograph toward Neptune. They were originally planning to study the planet's atmospheric circulation. What they found instead astonished them. Clear, unmistakable auroras, glowing cyan splotches of light high in Neptune's upper atmosphere. The first confirmed detection of auroral activity on the solar system's most distant major planet. One researcher who had spent years searching for this signal described being stunned by the detail and clarity. After decades of failure, the discovery came almost casually, during observations intended for different purposes entirely. But the auroras themselves presented immediate puzzles. On Earth, auroras cluster around the magnetic poles. Charged particles from our star spiral along magnetic field lines and strike the upper atmosphere near the Arctic and Antarctic. The collision excites atmospheric gases, which release energy as the shimmering curtains of green and red light we call the northern and southern lights. Neptune's auroras appear nowhere near its poles. They glow at mid-latitudes, the planetary equivalent of South America or Southern Africa. This bizarre location results from Neptune's extremely tilted magnetic field, which is offset by 47 degrees from the planet's rotation axis. Why Neptune's magnetic field is so misaligned remains unclear. The planet rotates on an axis tilted only 28 degrees from vertical, nearly identical to Earth's axial tilt. But its magnetic field points in a completely different direction, as if the planet's magnetic and geographic personalities are entirely disconnected. The Webb observations also revealed a critical chemical signature. For the first time at Neptune, astronomers detected trihydrogen cation, a molecule designated H3+. This ion forms when charged particles smash into hydrogen-rich atmospheres and serves as a definitive marker of auroral activity. Scientists had detected trihydrogen cation in the atmospheres of Jupiter, Saturn, and Uranus. Its presence at Neptune was expected, but had never been confirmed until Webb looked. Perhaps most puzzling was what the data revealed about Neptune's temperature. The planet's upper atmosphere has cooled dramatically since Voyager flew past. Several hundred degrees colder than measurements from 1989 suggested. This dramatic cooling may explain why the auroras remained hidden for so long. Colder temperatures mean fewer energetic particles, fainter emissions, and signals buried below the detection threshold of every instrument that tried before Webb. But why has Neptune cooled so much? The planet sits so far from our star that seasonal changes unfold over decades. Weather patterns may shift on timescales longer than human careers. Astronomers now plan to observe Neptune throughout an entire solar cycle, 11 years of study that may reveal how the distant world responds to changing conditions flowing outward from our star. Every answer the telescope provides seems to generate new questions. And closer to home, in the wreckage of a dead star, Webb has revealed structures no one anticipated. 340 years ago, a star exploded. The light from that catastrophic death reached Earth sometime in the late 1600s, though no contemporary observers recorded seeing anything unusual. The supernova's brilliance was apparently absorbed by thick dust clouds in the Milky Way before it could make an impression on earthbound eyes. Today, we call the expanding shell of debris Cassiopeia A. At 11,000 light-years away, it remains the youngest known supernova remnant in our galaxy, and the James Webb Space Telescope has transformed it into a laboratory for understanding how massive stars die. Previous observations from other telescopes revealed Cassiopeia A as a roughly circular bubble of hot gas, glowing in X-rays and radio waves. Hubble showed intricate knots and filaments in visible light, but Webb's infrared vision uncovered something entirely new. Deep within the remnant, projected against its interior, lies a structure no one had seen before, a thick sheet of material pockmarked with dozens of small, nearly circular holes. Because of its green appearance in the representative color images, astronomers nicknamed it the Green Monster. The discovery was completely unexpected. Supernova remnants are supposed to be hollow shells, the outer skins of exploded stars racing outward into space. The Green Monster sits in front of the main shell from our perspective, as if a veil had been draped across the cosmic wreckage. What is it? And where did those holes come from? Detailed analysis suggests the green monster is circumstellar material, gas and dust shed by the star before it exploded, now illuminated and sculpted by the blast wave that followed. The holes appear to be puncture wounds. Knots of high-velocity ejecta, chunks of the exploded star racing outward at thousands of kilometers per second, have punched through the sheet of circumstellar material like bullets through fabric. The research team measured more than 24 of these circular structures. Each spans roughly 1 to 3 arc-seconds on the sky. If our star were placed at the center of one hole, its boundary would lie near the inner edge of our solar system's Oort cloud. These are not small features, but Webb's discoveries at Cassiopeia A extended beyond the green monster. The telescope revealed a web-like network of unshocked ejecta filaments, material from the exploded star that has not yet encountered anything to disturb it. These ghostly threads preserve information about the star's final moments, the turbulent mixing that occurred as the core collapsed and the outer layers were flung into space. Webb also detected remarkably bright carbon monoxide emission. This molecule forms in the cooling debris of supernovae, but had never been observed at such high temperatures. The finding indicates carbon monoxide is being created and destroyed simultaneously, chemistry in action amid the chaos of stellar death. One researcher described spending the rest of his career trying to understand what lies in this dataset. The images contain more information than anyone anticipated. Perhaps most intriguingly, Webb found what astronomers call baby Cassiopeia A, a small smudge of light, a light echo, sitting 170 light-years behind the main remnant. This echo is illuminated by photons from the original explosion finally reaching a distant dust cloud and warming it to visibility. Light echoes allow astronomers to study ancient events as if they happened recently. The echo from baby Cassiopeia A contains information about the explosion itself, information that has been traveling through space for centuries. Supernovae matter to all of us personally. They created the heavy elements that make up our bodies, the calcium in our bones, the iron in our blood, the oxygen we breathe. All of it was forged in exploding stars and scattered across the cosmos in events like the one that created Cassiopeia A. Understanding how stars die is understanding our own origin story. And as astronomers study the remnants of dead stars, they are also watching new ones being born. In the delicate process of planet formation, the telescope has witnessed something remarkable. How did our cosmic neighborhood form? 4.5 billion years ago, a vast cloud of gas and dust collapsed under its own gravity. At its center, a young star ignited. Around it, a swirling disk of material remained, the raw ingredients that would eventually become planets, moons, asteroids, and comets. We call this structure a protoplanetary disk, and the James Webb Space Telescope is revealing these cosmic construction sites in unprecedented detail. One of the most famous targets is HL Tauri, a young star roughly 460 light-years away in the Taurus star-forming region. Previous observations from the Atacama Large Millimeter Array showed concentric rings and gaps in the disk surrounding this infant star, suggesting planets might already be plowing through the material. When Webb turned its infrared instruments toward HL Tauri, researchers expected to see the disk or perhaps detect forming planets within it. Instead, they saw something completely different, and it blew their minds. The telescope revealed streams of material flowing from the outer envelope of gas surrounding the young star down into the protoplanetary disk itself. Like rivers feeding a lake, these streamers carry raw material from the larger cloud into the region where planets form. We see a very complex and dynamic system, one researcher explained. Material flows from the outer envelope into the inner regions of the disk, where planets are being assembled. This process, called infall, had been theorized but never observed so clearly. The Webb images show it happening in real time. Our own cosmic neighborhood may have experienced exactly this kind of feeding during its earliest stages. But HL Tauri is not the only target. Webb has examined multiple protoplanetary disk systems, each revealing unique characteristics. Around the star MWC 758, previous observations had shown spiral arms forming in the disk. These patterns suggest a massive planet is orbiting somewhere within, its gravity disturbing the material like a spoon stirring soup. Webb's observations placed the most stringent constraints yet on where this suspected planet might hide. The data revealed no new planets directly, but the sensitivity is groundbreaking. Each non-detection narrows the possibilities, telling astronomers what kinds of planets can and cannot exist in these systems. In a separate breakthrough, Webb confirmed a long-proposed process of planet formation by observing water vapor in protoplanetary disks. The theory suggested that ice-coated pebbles drift from the cold outer regions of disks toward warmer inner zones. When they cross the frost line, where temperatures allow ice to vaporize, they release water vapor. Webb detected exactly this signature in compact disks around young stars. The observations represent the first direct confirmation of pebble drift, a fundamental process that may explain how rocky planets like Earth accumulate their mass. The telescope also discovered that protoplanetary disks lasted longer in the early universe than they do today. In metal-poor environments resembling conditions billions of years ago, disks around young stars appear to persist for extended periods. This extra time would have given planets more opportunity to form, potentially explaining some of the unexpectedly mature structures Webb has detected in ancient galaxies. Perhaps most surprising was what Webb found around brown dwarfs, objects too small to be stars but too large to be planets. In the Orion Nebula, the telescope confirmed that 20 of these failed stars possess their own protoplanetary disks. This means planets might form even around the smallest and dimmest stellar objects. The universe's capacity for world building extends far beyond what anyone imagined. Each observation teaches us something about how cosmic neighborhoods assemble. Every disk is a laboratory, every streamer is a clue, and sometimes the telescope spots the finished product directly, an actual planet, captured in its portrait for the first time. After 3 years of operation, it finally happened. On June 25, 2025, astronomers announced that the James Webb Space Telescope had discovered its first exoplanet, not by watching a star dim as a planet crossed in front, not by measuring gravitational wobbles, but by actually seeing the planet itself, glowing faintly in the infrared darkness of space. The world is called TWA-7b. It orbits a young star, 111 light-years from Earth, and it represents a milestone in the telescope's scientific legacy. Direct imaging of exoplanets is extraordinarily difficult. Stars are millions of times brighter than the worlds that orbit them. Their overwhelming light drowns out any faint planetary glow. Trying to see an exoplanet next to its host star has been compared to spotting a firefly next to a searchlight from miles away. Webb overcame this challenge using a coronagraph, an instrument that blocks out a star's light, like the moon blocking our star during an eclipse. With the stellar glare suppressed, faint objects nearby can emerge from the darkness. The Discovery team, led by researchers at the French National Center for Scientific Research, focused on young stars with debris disks that could be viewed face-on from Earth. This orientation allows astronomers to see the full disk structure rather than just its narrow edge. The star TWA-7, also known as CE Antilles, fit these criteria perfectly. Previous observations had revealed 3 distinct rings in its debris disk, with gaps that hinted at unseen planets sculpting the material. When Webb examined the narrow middle ring in June 2024, it detected a faint infrared source. After eliminating observation errors and confirming the detection was real, the team concluded they had found a planet. TWA-7b is approximately the mass of Saturn. This makes it 10 times lighter than any exoplanet previously captured in a direct image. The discovery demonstrates that Webb can detect worlds far smaller than the massive gas giants imaged by earlier telescopes. Computer simulations confirmed the finding. When researchers modeled a Saturn-mass planet at the detected location, the simulations produced exactly the thin ring and gap structure observed in the debris disk. The planet's gravity is shaping its environment in predictable ways. The world is young, likely only a few million years old. Because recently formed planets are still hot from the energy of their creation, they glow more brightly in the infrared than older, cooler worlds. This thermal signature is what Webb detected. One researcher described the discovery as likely just the beginning. The telescope has the potential to image even smaller planets in the future, perhaps worlds with only 10% of Jupiter's mass. This capability opens new frontiers. Previous direct imaging could only spot massive, hot planets orbiting far from their stars. Webb can now probe closer separations and smaller sizes, approaching the range where rocky worlds might eventually become visible. The finding also demonstrates that planets can shape debris disks in observable ways. By studying how disks respond to planetary gravity, astronomers can infer the presence of worlds too faint to see directly. TWA-7b will not be the last. The telescope continues examining young stellar systems, searching for the faint glows of newborn worlds. Each discovery adds to our census of planetary systems and reveals the diversity of outcomes when gas and dust collapse around infant stars. But while Webb finds new worlds around distant stars, it may have also discovered one much closer to home, a planet that appeared, then vanished, around our nearest stellar neighbor, 4 light-years. That is the distance to Alpha Centauri, the nearest stellar system to our own. In cosmic terms, it is practically next door. A trip at the speed of light would take only 4 years. At the speed of our fastest spacecraft, it would take tens of thousands of years, but at least the destination is conceivable. For decades, astronomers have searched for planets around these nearby stars. 3 confirmed worlds orbit Proxima Centauri, the faint red dwarf in the system. But Alpha Centauri A and B, the 2 bright stars that form a binary pair, have resisted planetary detection. In August of 2024, the James Webb Space Telescope changed that, using its mid-infrared instrument and a coronagraph to block stellar light. Astronomers detected a faint object near Alpha Centauri A, an object more than 10,000 times fainter than the star itself. The initial excitement was enormous. If this was a planet, it would be the closest to Earth orbiting in the habitable zone of a star similar to our own. A gas giant, yes, but potentially surrounded by moons where liquid water might exist. Then the planet vanished. Follow-up observations in February and April of 2025 found nothing. The telescope pointed at the same location, used the same techniques, and saw no trace of the object detected months earlier. "We are faced with the case of a disappearing planet," one researcher exclaimed. The mystery sent astronomers scrambling to their computers. Using simulations that incorporated every piece of data, including observations from ground-based telescopes dating back to 2019, they modeled millions of potential orbits. The solution they found was elegant but frustrating. In half of the stable orbital configurations that matched all the observations, the planet would have been too close to its star during the follow-up observations to be visible, hidden in the stellar glare rather than absent from the system. Based on the brightness of the initial detection and the orbital constraints, researchers believe the object is a gas giant roughly the mass of Saturn. It orbits Alpha Centauri A on an elliptical path that brings it between 1 and 2 times the distance between Earth and our star. This orbit places the planet within Alpha Centauri A's habitable zone, the region where temperatures might allow liquid water on a solid surface. But as a gas giant, the planet itself could not support life as we know it. Any moons it possesses, however, are a different matter. The discovery, if confirmed, would be the closest directly imaged exoplanet, the coldest and oldest world captured in such a portrait. and the nearest habitable zone planet around a star resembling our own. But confirmation requires patience. The planet's orbit, if the models are correct, would bring it back into visible range in August of 2026. Astronomers are already planning observations for that window. The existence of such a planet in a binary star system would also challenge our understanding of planetary formation. The gravitational influence of two closely separated stars creates chaotic environments where planets were thought to have difficulty forming or surviving. If this world is real, it has persisted despite those challenges. One researcher noted that its very existence would force revisions to theories of how planets form, survive, and evolve in such environments. The waiting continues. The data sit in archives, analyzed and reanalyzed. The models run endlessly, testing every possible configuration. Is there a gas giant orbiting our nearest stellar neighbor? A world with potential moons where life might one day be found? The universe has answered with ambiguity, and so we watch and wait and wonder. Meanwhile, the telescope continues its search for atmospheres around small, rocky worlds, including the most promising candidate for habitability yet studied. 40 light-years away, 7 Earth-sized worlds orbit a dim red star. The TRAPPIST-1 system has captivated astronomers since its discovery in 2017. No other known system contains so many terrestrial planets packed so closely together. 3 of them orbit within the star's habitable zone, where liquid water might persist on their surfaces. Of these 3, TRAPPIST-1e has emerged as the most intriguing. Its size, mass, and density closely match Earth's. Its distance from its star allows moderate temperatures. If any world in this system could support an ocean, TRAPPIST-1e is the leading candidate. But there is a catch. For liquid water to exist, the planet must have an atmosphere. Without a blanket of gases to trap heat and regulate temperature, any surface water would freeze or evaporate into space. Does TRAPPIST-1e have an atmosphere? The James Webb Space Telescope has been working to answer this question since it began science operations. The results so far are tantalizing but inconclusive. Using the near-infrared spectrograph, astronomers observed TRAPPIST-1e as it passed in front of its star. This technique, called transmission spectroscopy, searches for chemical fingerprints in starlight filtered through a planet's atmosphere. If gases are present, they absorb specific wavelengths, leaving telltale signatures in the spectrum. The initial observations ruled out several possibilities. TRAPPIST-1e does not possess a thick, hydrogen-rich atmosphere like the primordial envelopes surrounding newly formed gas giants. If it ever had such an atmosphere, intense radiation from its active red dwarf star has stripped it away. This is not surprising. Red dwarf stars are violent, especially when young. They emit powerful flares that can blast away atmospheric gases over millions of years. The inner planets of TRAPPIST-1 have been subjected to this radiation for billions of years. But Earth-like planets can build secondary atmospheres. Volcanic eruptions pump gases from planetary interiors. Outgassing releases trapped volatiles. Our own world lost its primordial atmosphere and constructed a new one over time. The Webb data hint that TRAPPIST-1e might have done the same. Researchers detected possible signatures consistent with a nitrogen-rich atmosphere containing traces of methane. Such a composition would resemble Saturn's moon Titan, a world with thick haze layers and surface liquids. However, the detection is not definitive. The star, TRAPPIST-1, is extremely active, with surface features that contaminate the spectra. Astronomers are trying to measure. Separating planetary signals from stellar noise requires extraordinary precision and extensive observations. Additional observations are already planned. 15 more transit measurements have been scheduled, with astronomers hoping to build enough statistical confidence to distinguish real atmospheric features from noise. If successful, the detection would represent a historic achievement. The first confirmed atmosphere on a potentially habitable world beyond our cosmic neighborhood. A target for future observations, searching for biosignatures, the chemical fingerprints of life. One researcher described the work as pushing the limits of what the telescope was designed to do. Webb was conceived before the TRAPPIST-1 system was even discovered. That it can study these worlds at all is a testament to its remarkable capabilities. The search continues. Each transit provides more data. Each analysis refines our understanding. Somewhere in the noise may lie evidence that changes everything we believe about our place in the universe. And while astronomers probe distant atmospheres, Webb has revealed something remarkable about how stars themselves are born. A cosmic alignment that confirms theories physicists have held for decades. Sometimes the universe provides exactly the evidence scientists need. For years, astronomers had theorized that as interstellar clouds collapse to form stars, the resulting objects should spin in similar directions. Angular momentum, the rotational energy contained in a swirling gas cloud, should be conserved and passed down to the stars that emerge from it. But directly observing this prediction proved challenging. Young stars form shrouded in dust. Their rotation axes are difficult to determine. Confirming that multiple stars share aligned spins required seeing something that had remained hidden. Then, the James Webb Space Telescope imaged the Serpens Nebula. This stellar nursery sits roughly 1,300 light-years from Earth. It is young by cosmic standards, only 1 or 2 million years old. Stars are actively forming within its dusty depths, emerging from their cocoons into the harsh light of space. When Webb's near-infrared camera captured the nebula's northern region, astronomers noticed something remarkable. A group of protostellar outflows, jets of gas blasting from newborn stars, all pointed in the same direction. Typically, such jets have varied orientations. Each star should have its own random rotation axis, and its jets should align with that axis. Seeing multiple jets slanted the same way, to the same degree, suggested something deeper was happening. These aligned outflows are like sleet pouring down during a storm, one researcher explained. They provide a historical record of the fundamental way that stars are born. Young stars shoot supersonic jets from their poles as they gather mass. These jets collide with surrounding gas and dust, creating bright shock waves visible in infrared light. The direction of each jet reveals the rotation axis of its source star. In the Serpens Nebula, a cluster of particularly young stars, some only about 100,000 years old, all share similar rotation orientations. They inherited their spins from the collapsing cloud that formed them. This confirmation has implications beyond basic physics. Aligned rotation might affect how planetary systems form and evolve. It might influence the likelihood of binary star formation. It might even affect the stability of any worlds that eventually emerge from the surrounding debris. Webb is a young stellar object finding machine, another researcher declared. In this field, we pick up signatures of every single young star, down to the lowest mass objects. The Serpens Nebula observations revealed other surprises as well. Filaments and wisps of different colors trace reflected starlight from protostars still embedded in their birth clouds. Diffuse orange regions mark dust, sitting in front of these reflections. The image tells the complete story of star formation in progress. The telescope found stars at every stage of development, objects still wrapped in thick cocoons of material, stars just beginning to emerge, fully formed young systems already dispersing their natal clouds. Each observation adds to a coherent picture of how stellar nurseries operate. The process is messier than simplified models suggested, more dynamic, more varied. But fundamental principles, like angular momentum conservation, hold true. The universe plays by consistent rules, and those rules are becoming clearer with each image the telescope returns. From the Serpens Nebula to the Carina Nebula, stellar birth sites across the sky are surrendering their secrets. One of the first images the James Webb Space Telescope released changed how humanity saw the universe. The cosmic cliffs, a wall of gas and dust rising like mountains against a star-studded sky. Behind it, hidden from previous telescopes, lay something extraordinary, newborn stars by the hundreds. The image shows a region within the Carina Nebula, roughly 7,600 light-years from Earth. What appears to be a landscape of peaks and valleys is actually the edge of a massive stellar nursery. The cliff face marks the boundary between denser gas, where stars form, and the cleared cavity carved by radiation from mature stars. Previous telescopes could see the cliff itself, but could not penetrate it. Webb's infrared vision changed everything. Behind the curtain of dust, the telescope revealed protostars still gathering mass, objects that had never been observed before, wrapped in shrouds that blocked visible light but allowed infrared wavelengths to escape. Each glowing point marked a star in the process of being born. The image also captured jets and outflows from these hidden babies, streams of material ejected at high speeds, colliding with surrounding gas, creating patterns that trace the violence of stellar formation. But the cosmic cliffs did more than reveal hidden stars. They demonstrated the interplay between destruction and creation that drives cosmic evolution. The radiation from nearby mature stars is eroding the cliff face. Gas boils away under the intense bombardment. Over millions of years, the cliff will retreat, exposing more of the dense gas behind it to the harsh stellar environment. As the erosion proceeds, it compresses gas at the boundary. This compression triggers gravitational collapse. New stars form precisely because the cliff is being destroyed. The same process operates in the pillars of creation and countless other stellar nurseries across the galaxy. Radiation from one generation of stars seeds the formation of the next. Destruction enables creation. The Carina Nebula is one of the largest and brightest nebulae in the night sky. It contains enormous quantities of gas and dust, enough raw material to form thousands of stars over millions of years. Webb's observations are mapping this inventory in unprecedented detail. Beyond the cosmic cliffs, the telescope has examined other regions within Carina. Each observation reveals new protostars, new outflows, new structures that challenge and refine models of star formation. The early release of this image was strategic. It demonstrated what the telescope could do. It captured public imagination. It announced that a new era of astronomy had begun. But the scientific value extends far beyond public relations. The data contain information about stellar masses, formation rates, chemical compositions, and evolutionary stages. Researchers will study these observations for years, extracting insights that illuminate how the galaxy renews itself. Every star that forms will eventually die. Some will explode as supernovae, scattering their heavy elements into space. Others will fade quietly into white dwarfs, their outer layers drifting away as planetary nebulae. A few will collapse into neutron stars or black holes. But from the debris of stellar death, new stars will rise. The cycle continues, has continued for billions of years, will continue for billions more. The cosmic cliffs show us one moment in this eternal dance. And the telescope that captured them continues its mission, revealing more with each passing day. 3 years. In just 3 years of scientific operations, the James Webb Space Telescope has transformed our understanding of the cosmos. It has challenged theories held for decades. It has revealed objects that should not exist. It has shown that the universe is stranger, older, and more dynamic than anyone imagined. But this is only the beginning. The telescope was designed to operate for at least 5 years, with fuel reserves that could extend its mission to 20 years or more. If nothing breaks, if the instruments continue functioning, Webb will keep observing for decades to come. What will it discover? In the near term, astronomers will continue probing early galaxies, searching for the very first stars and black holes to emerge after the Big Bang. They will map the chemical evolution of the cosmos, tracing how heavy elements spread from supernovae into new generations of stars and planets. They will study supermassive black holes at cosmic dawn, testing theories of how these monsters grew so massive so quickly. The heavy seeds hypothesis, black hole stars, direct gas collapse. Each prediction makes specific claims that Webb can evaluate. The mystery of the Hubble tension will receive continued attention. Is the universe expanding faster than our models predict? Is early dark energy the solution? Does dark energy change over time? The telescope's observations constrain these possibilities and may eventually force a resolution. Closer to home, Webb will continue examining exoplanet atmospheres. The search for biosignatures on TRAPPIST-1e and similar worlds represents one of the most profound scientific pursuits in human history. Finding evidence of life beyond Earth would change how we see ourselves forever. The candidate planets at Alpha Centauri and TWA7 require confirmation. Additional observations will determine whether these worlds are real or mirages created by noise in the data. If real, they become targets for intensive study. Webb will also keep watching stellar nurseries form new stars and planetary systems. Each protoplanetary disk reveals something about how worlds assemble from dust and gas. Each observation refines our understanding of our own cosmic history. The telescope's capabilities are still being explored. Engineers and scientists continue developing new techniques, pushing instruments beyond their original specifications. Discoveries still unimagined may emerge from these efforts, but Webb is not alone. The Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will complement Webb's observations with wide-field surveys. Ground-based facilities like the extremely large telescope under construction in Chile will provide additional perspectives. A new generation of astronomers is rising to interpret these observations. Students who were children when Webb launched will spend their careers analyzing its data, making discoveries that build on what we learn today. The questions Webb addresses are ancient. Are we alone? How did the cosmos begin? What will happen in the end? Humans have asked these questions since we first looked up at the night sky and wondered. Now, for the first time, we have instruments capable of providing answers. The journey of discovery is accelerating. Each observation reveals new mysteries. Each mystery drives new observations. The cycle feeds itself, pushing knowledge forward. We live in an extraordinary moment. A telescope floating 1 million miles from Earth is reshaping our understanding of everything. Stars, galaxies, black holes, planets, the expansion of space itself. The universe is not what we thought, but perhaps that is the point. Perhaps the greatest discoveries are the ones that force us to think again, to question assumptions, to rebuild our picture of reality from improved foundations. The James Webb Space Telescope has given us that gift, and the journey continues.